Hello students, welcome to my channel Arun's Physics Portal. In this lecture, I will be discussing about network and transfer functions and poles and zeros. This topic is meant for MSc Physics and Electronics students and also for BE and BTech students of EEE and EC branches. The JRF and NET aspirants will also find this topic useful. The complete note of the topic is given here for your convenience. I hope you enjoy going through it. Now let us come to the topic. A network is simply an interconnection of circuit elements like resistors, capacitors, inductors, diodes, transistors, FETs, MOSFETs and so on and so forth. एक नेटवर्क को हम रिप्रेजेंट करते हैं एक रेक्टेंगुलर बॉक्स से. इसे हम बोलते हैं ब्लैक बॉक्स because we are not at all concerned with what is inside that box. We are simply concerned with its terminal properties. And terminals are required to connect any network to any other network, or taking some measurements to such associated terminals are called terminal pair or ports. यदि किसी नेटवर्क में एक ही पेयर ऑफ टर्मिनल है तो इसे हम बोलते हैं वन पोर्ट नेटवर्क. ये दो पेयर ऑफ टर्मिनल्स हैं तो इसे हम बोलते हैं टू पोर्ट नेटवर्क. करंट और वोल्टेज को रिप्रेजेंट करते हैं आई और वी से. सो इन फिगर 1a वी हैव शोन यू वन पोर्ट नेटवर्क. देखिए ये हमारा वन पोर्ट नेटवर्क है. इसके अंदर क्या है ये हमें पता नहीं है. हाउ दे आर कनेक्टेड ये भी हमें पता नहीं है. We simply know that we have an input voltage V applied here and we have an input current I. So this is energy source and this is the resulting current. This is a one port network because we have here only one pair of terminals. In figure 1b, we have two pair of terminals. This is one pair and this forms another pair. We have an input voltage V1 here and the resulting current is I1. At the output, we have the voltage V2 and the current is I2. So this is a two-port network because we have here two pair of terminals. Okay. Now let us see what are driving point functions. If the excitation and response are measured at the same port, then the network function is known as driving point function. If we have only one port network, then we have only one voltage and only one current. And therefore, only one network function or its reciprocal can be defined. एक ही port है, that means we have only one pair of terminals where we can have only one voltage and one current. तो हम इसमें सिर्फ एक ही तरह के नेटवर्क फंक्शन को या उसके रेसिप्रोकल को डिफाइन कर सकते हैं. So the first one is driving point impedance function. It is defined as the ratio of the voltage transform at one port to the current transform at the same port. It is denoted by Zs. Thus, Zs is Vs upon Is. So the numerator is voltage and the denominator is the current. So ratio of voltage upon current is the impedance. Okay. So this is known as driving point impedance function. Second is driving point admittance function. It is defined as the ratio of the current transform at one port to the voltage transform at the same port, and it is denoted by Ys. Thus, Ys is Is upon Vs. I is the current, V is the voltage. So this is the reciprocal of resistance or impedance. So this is called admittance. Okay, now we come to transfer function. A transfer function or transmittance is a system function for which the variables are measured at two different ports. Assume कीजिए कि we have a two-port network. That means we have two pair of terminals. Okay. So in this case, the transfer function relating the voltage and the current may have any one of the following possible forms. First one is the ratio of one voltage to another voltage, which is called voltage transfer ratio. हमने देखा पहले कि टू पोर्ट नेटवर्क में एक इनपुट पोर्ट है, एक आउटपुट पोर्ट है। इनपुट पोर्ट पे वोल्टेज भी है, करंट भी है, आउटपुट पोर्ट पर भी वोल्टेज है, करंट है। सो द रेशियो ऑफ वन वोल्टेज टू अनदर वोल्टेज इज कॉल्ड द वोल्टेज ट्रांसफर रेशियो। ठीक है, दो वोल्टेज है, एक इनपुट में एक आउटपुट में, उसके रेशियो को हम बोलते हैं वोल्टेज ट्रांसफर रेशियो। सेकेंड इज the ratio of one current to another current, which is called the current transfer ratio. Okay. Third is the ratio of one current to another voltage, called transfer admittance, or the ratio of one voltage to another current, called transfer impedance. ठीक है, ये तीन तरह के ट्रांसफर फंक्शन हम डिफाइन करते हैं। So, although the transfer function may be defined in any one of the above given ways, it is conventional to define it as the ratio of one output quantity to one input quantity. Following this convention, we define the following four transfer functions for the two-port network shown in figure 2. So this is our two-port network. This is the input port, this is output port. The input voltage is V1, the input current is I1, output voltage is V2, and the output current is I2. So first we define the ratio of output voltage to input voltage. Symbolically, we write it as G1 to S. V2 is output voltage, V1 is input voltage. So this is the voltage gain. Because both the numerator and denominator are measured in volt, this quantity is non-dimensional. So this is known as non-dimensional voltage gain. Second is the ratio of output voltage by input current. So numerator is voltage, output voltage, and denominator is input current. So ratio of voltage by current is impedance. So this is impedance because V2 is measured at the output port and I1 is measured at the input port. This is known as transfer impedance and we denote it by Z1 to S. Clear? Now, the third one is the ratio of output current to input voltage. So न्यूमरेटर में हमारा करंट है और डिनोमिनेटर में वोल्टेज है. So this is the ratio of current upon voltage. So this is the reciprocal of resistance or this is admittance. Since this quantity is measured at the output port and V1S is measured at the input port, this is known as transfer admittance. And this is denoted by Y1 to S. And the last is the ratio of the output current upon the input current. Since both the numerator and denominator have the dimension of ampere, so this is a non-dimensional current gain. This is denoted by alpha 1 to S. Clear? So the impedance or admittance, which is the reciprocal of impedance, found at a given port is called a driving point impedance or admittance. Because of the similarity of impedance and admittance, and to avoid writing impedance and admittance, the two quantities are assigned a single name, immittance, which is a combination of impedance and admittance. And immittance is thus an impedance or an admittance. तो impedance और admittance के लिए common हम word use करते हैं immittance. Now let us see how the network functions can be calculated. So first we take the case of circuit shown in figure 3. In this figure, we have a resistor R, an inductor of inductance L, and a capacitor or capacitance C connected in series. And we have to find out the impedance between the points A and B. We see here that R, L, and C, all of them are connected in series. So the total impedance between the points A and B is equal to ZS equal to R plus SL plus 1 upon SC. Okay, so take the LCM of this. This is SC, this is RCS plus S square LC plus 1. Now take out L common from the numerator. This is L here. Within bracket we have now S square plus R upon L into S plus 1 upon LC divided by S. We see that ZS is a ratio of two polynomials. The numerator is a polynomial in S of second degree, while the denominator is a polynomial of first degree. Okay? Now see the next example. In figure 4, we have a resistor and an inductor connected in series. With this series connection, we have a capacitor of capacitance C connected in parallel. So we have to find out the driving point impedance between the points A and B. Now see, the equivalent resistance of this R and this will be how much? This will be R plus SL. Okay, with this series combination of R and L, we have a capacitor C in parallel. So if ZS be the equivalent impedance between the points A and B, then we can write 1 upon ZS is equal to 1 upon R plus SL plus 1 upon 1 by SC. So this is equal to 1 upon R plus SL plus SC, and therefore ZS is 1 upon SC plus 1 upon R plus SL. Okay, this is what we have written here. Clear? So from this expression, take out C common from the denominator. So this leaves us 1 upon S plus 1 upon RC plus SLC. If you go on simplifying this comes out to be 1 upon C within bracket S plus R upon L divided by S square plus R by L into S plus 1 by LC. Here again we see that ZS is a ratio of two polynomials. The numerator is a polynomial in S of first degree, whereas the denominator is polynomial in S of second degree. Now consider example 3. We have shown a two-port network. This is one port and this is another port. Between the points A and B, we have a resistor R and a capacitor C connected in series. V1s is input voltage and V2s is the output voltage across the capacitor. Okay, let us assume that the current that flows through this is Is. Okay, and therefore V1s will be equal to RIs plus 1 upon SC into Is, and V2s is equal to 1 upon SC into Is. The voltage gain is thus G12s equal to V2s upon V1s. This is equal to 1 upon SC Is divided by Is into R plus 1 upon SC into Is. So Is cancels out throughout. So this is 1 upon SC divided by R plus 1 upon SC. Or we can write G12S equal to 1 upon SRC plus 1 equal to 1 upon RC divided by S plus 1 upon RC. So in this case also, we see that G1 to S is the ratio of two polynomials. The numerator is a polynomial in S of degree 0. Note that S to the power 0 is equal to 1. You can write here S to the power 0, which is nothing but equal to 1. And the denominator is a polynomial of degree 1 in S. Clear? Next, we come to figure 6, where we have a resistor R1 in parallel with a capacitor or capacitance C. Okay, with this parallel combination, we have resistor R2 in series. This is a two-port network. This is the input port and this is the output port. The output is taken across the resistor R2. Clear? In this figure, we have a resistor R1 and a capacitor C connected in parallel. Okay, so if Z dash be the equivalent impedance of these two in parallel, then we have 1 upon Z dash is 1 upon R1 plus 1 upon SC1 equal to 1 upon R1 plus SC1, and therefore Z dash is 1 upon 1 by R1 plus SC1, or this is equal to R1 divided by 1 plus S R1 C1. Okay, and therefore the impedance between the points A and B is equal to Z dash plus R2. So we have Zs is R1 upon 1 plus R1 Cs plus R2. The input and output voltages V1s and V2s are respectively given by V1s is Zs into Is, where Is is the current that flows in the loop, and V2s is R2s into Is. The voltage gain, that is the ratio of output voltage upon input voltage, is G12s is V2s upon V1s. Put the value of V2s and V1s here. So this is R2 into Is upon Zs into Is. This one cancels out here. This cancels out. And we get G12s is R2 upon, put the value of Zs is R1 upon 1 plus R1 Cs plus R2. So this is, when simplified, gives you S plus 1 upon R1C divided by S plus R1 plus R2 upon R1 R2C. So in this transfer function also, both the numerator and denominator are of the same degree in S, and that is 1. Okay, so all the network functions we have calculated are thus seen to be the quotient of two polynomials in S and can be expressed in the general way as Ns is Ps upon Qs equal to A naught s to the power n plus A1 s to the power n minus 1 plus A2 s to the power n minus 2 plus A n minus 1 s plus An divided by A naught s to the power m plus B1 s to the power m minus 1 plus B2 s to the power m minus 2 plus Bm minus 1 s plus Bm, which is a rational function of S. In this equation 1, n is the degree of polynomial of the numerator and m is the degree of polynomial of the denominator. The coefficients a and b are real and positive for network of passive elements and no controlled sources. Now let us see what are the poles and zeros of network functions. Okay, so we have seen that all the network functions can be expressed in the form of a quotient of polynomial in S, having the general form as given by equation 1. The equation Ps equal to 0 has n roots and Qs equal to 0 has m roots. Therefore, both Ps and Qs may be expressed as a product of linear factors involving these roots, and hence equation 1 can also be expressed as Ns is equal to h times within bracket s minus z1 into s minus z2 dot 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 s minus zn divided upon s minus p1 into s minus p2 dot s minus pm, where h is equal to a naught upon b naught is a constant, and this is known as a scale factor. Z1, Z2, Zn are complex frequencies, and so are P1, P2, and P3 up to Pm. For S equal to Z1, Z2 up to Zn, the network function vanishes. It is obvious from equation 2. These frequencies are known as the zeros of the network function. Z के जिस वैल्यू पर ns का मान 0 हो जाए उसे हम बोलते हैं zero of the network function. When S is equal to P1, P2 up to Pm, the network function becomes infinite. These frequencies are known as the poles of the network function. At any other value of the complex frequency other than 0 and pole, the network function has a finite non-zero value. In the above equation, the factor s minus zj are known as the zero factors, and the factors s minus pj are known as the pole factors. When r poles or zeros in equation 2 have the same value, the pole or zero is said to be of multiplicity r. If a pole or zero is not repeated, it is said to be distinct. Poles or zeros at s equal to infinity are also assigned a degree. When n is greater than m in equation 1, the pole at infinity is of degree n minus m. When n is less than m in equation 1, the zero at infinity is of degree m minus n. So this is all about the network and transfer functions, the poles and zeros, and how to find out the poles and zeros of a network function. I assume you like this presentation. यदि आपको मेरा यह प्रेजेंटेशन अच्छा लगा हो तो इसे लाइक करें, शेयर करें और मेरे चैनल को सब्सक्राइब करें. So thank you for watching. See you next time with some other topic of interest. Till then, goodbye.